Good evening. Our project is called AutoGrow, an IoT plant cultivation data analysis system. The core question we try to answer is, can a machine learning model automatically detect what growth state a plant is in, just from sensor readings, without anyone physically checking it? So we had three goals. First, predict plant growth stage, seedling, vegetative, or bloom from sensor data alone. Second, enrich that data by pulling indoor weather from OpenMeteor API and fusing it with indoor readings. Third, and most importantly, be exhaustively honest, meaning we try every reasonable model and strategy and measure whether the data can actually support the task or whether the scores are just noise. Our data came from three tables. The main AutoGrow sensors table has 1,569 rows recorded every 10 minutes. Columns like temperatures, humidities, soil moistures, and light intensity, and the growth state label. Then two outdoor weather tables from OpenMeteor with 98 current snapshot and 192 hourly history record from Bangkok. All three needed to be timestamp aligned before we could use them together.
This data is complex along 5 dimensions simultaneously. First is time series. Every reading depends on the previous one, so you cannot shuffle rows like a normal data. Second is multimodal. 3 different sources with different formats and time granularities. Third, classes are imbalanced. Seedling makes up to 60% of reading, so a lazy model just predicts seedling every time and looks accurate while being used late. Fourth, the sensors are noisy. For example, like the Temp2 sensors recorded 0 degrees Celsius in 96 out of 1,569 readings, which is physically impossible for a leaf row environment. And the last one, we have mixed data types like numbers, binary flags, text label, and timestamp all in one dataset. This is actual sensor data over time. Each panel is one sensor and the dashed virtual lines make each state transition. The direct application is smart indoor farming. Automatically knowing the growth state means you can automate watering, lighting, and predict harvest time without a human physically inspecting the plant every day. But the same pipeline applies broadly. The same time series classification approach works for predictive maintenance in factories, patient health monitoring from wearables, and water quality monitoring in aquaculture.
Our pipeline has 8 stages. We load CSV, detect and standardize columns named automatically, remove outliers using both IQR and isolation forest, engineer features, filter noisy transition rows, and select the best feature using mutual information trains or model. And finally, evaluate with shape. Beyond course additions, we added 4 techniques beyond the course syllabus. Isolation forest detects multivariate anomalies. Combinations of sensor readings that are individually normal but suspicious together. Mutual information feature selections with different numbers of features to find the optimal count. Hierarchical KNN is the 2-step classifier that first separates seedling from everything else, then separates vegetative from bloom, exploiting the biological ordering of stages. Ordinal HGBR treats the stages as ordered, integers rather than unrelated categories. For the data exploration, here's the real class distribution. Seedling has 935 rows, blooms had 336, and vegetative had 297. There's a 3-to-1 ratio of seedling to others. This is why we use macro average F1, and as our metric, it weights all 3 classes equally, so a model can cheat by just predicting seedling more.
These blog posts show each sensor's value split by growth stage. The key insight here is the heavy overlap between vegetative and bloom. Look at temperature and humidity. The boxes are nearly on top of each other. Light intensity shows more separation. Bloom tends to get higher light. But overall, this chart is a visual warning that distinguish vegetative from bloom will be the hardest part. We also pull outdoor weather and merge it with indoor readings. You can see indoor temperature is consistently about 6 to 7 degrees cooler and much more stable than outdoor. The enclosure buffers the plant from outside heat. The Pearson correlation is 0.58, so outdoor weather provides context but doesn't independently explain what's happening inside. This heat map shows linear relationship between all numeric columns. Stage has moderate correlation with several sensors, which is promising. The high correlation between harvest ETA days, health score, and stage is actually a warning. Those columns encode the answer and had to be explicitly dropped to prevent data leakage. To summarize the explanation, seedling dominates. Vegetative and bloom overlap heavily in sensor space. Indoor temperature tracks outdoor but stays cooler, and soil moisture correlates strongly with humidity at 0.71.
So for feature engineering, a single sensor reading tells the model almost nothing but which growth state the plant is in, because growth stages are defined by sustained patterns over hours and days, not a single moment. So we engineer about 100 features, lags up to 12 steps back so the model can see sensor history, rolling means, and standard deviations to capture trends, delta features for rates of change, interactions terms like temperature times humidities, and cyclical time encoding. Crucially, all these only look backward, never at future. For feature selection and transition filter, with 100 features and only 830 training roles, we would overfit easily, so we use mutual information select k-base to sweep k values from 8 to 32 to find which features count give the base cross-validation F1. The yellow bar k equals 16 score 1.0 with 0 standard deviation, which is the same small fault artifact we saw with HG boost. The honest base is k equal to 20 at 0.875. We also drop rows near stage transition during training because those boundaries rows carry ambiguous labels. The sensors may still reflect the previous stage. And for the model zoo, we train 11 models in total under identical conditions, same train test split, same pre-processing, same metrics. Baseline are logistic regressions and decision tree. And the tuned one are KNN with tighter neighborhood, and the advanced one are random forest extra tree and his gradient boosting, SVC with RBF kernel and HG boost, and two novel strategy, hierarchical KNN and ordinal HGBR. The advanced and novel models are shown here. The keys one to remember are hierarchical KNN and our two-step biological classifier, and ordinal HGBR with three stages as ordered sequence rather than independent categories.
Before we look at results, let's understand what the base model actually learned. This is the sharp feature importance chart. The number one feature is temp-humidity interaction. The combined signal of temperature and humidity together, followed by the down cost, which is day of week encoded as a cosine. Then indoor humidity, light hours today, and like values. This tells us the model learned cumulative exposure patterns, how much light and humidity the plant experiences over time, not just what the sensors read right now. The fact that day of week ranks high suggests the grow room has a weekly lighting schedule the model picked it up on. These confusion metrics show what each model actually predicted versus reality. The pattern is the same across all models. They correctly identify most seedling rows, but they fail completely at separating vegetative from bloom. Every model predicts only seedling and vegetative. No model successfully predicts bloom as a distinct class. This is the vegetative bloom overlap problem we identify in the box plot. KNN does best at catching vegetative. The hierarchical KNN uses biological ordering to slightly improve bloom separation. Here are the finals holdout score. The best model is hierarchical KNN at 0.35 micro F1. KNN tune, Ester 3, and SVC are all around 0.317. The weakest is decision tree at 0.21. All scores are modest, but this is on a truly held-out test set. never touched during training. The spread from 0.21 to 0.35 tell us model choice does matter, but not dramatically.
Why are scores still modest even after this exhaustive pipeline? 3 reasons, rooted in data itself. First, vegetative and bloom are both measured plant stage. They look nearly identical to sensors. Second, growth state and transition are gradual, not sharp. Row near boundary are genuinely ambiguous. Third, after cleaning and splitting, we have about 830 training rows against 100 engineered features, which is a tight fit. The pipeline is not the bottleneck. We verify that the bottleneck is the data. So, for the 3-version evaluation, we iterate through 3 versions. The version 1 is the baseline. With basic feature engineering for models, the problem is that a code bug where XGBoost entry was overwritten, label-derived column presenting a leakage risk, and sharp crashing. And the version 2 fixed the code bug, added the Open Meteor API fallback, and expand feature to 100, and added feature pruning, still had the wedge bloom overlap problem. And for the last version, the exhaustive version, added CSV caching since our database was reached its limit, so we could not fetch the data from the database, so we use CSV instead. And we implement transition row filtering, manual information feature selection, and explicit leaky column block list. 9 models including our 2 novels one, and dynamic cross-validation. Base F1 reached 0.35. Remaining problem is that the dataset itself limits further improvement. So in summary, we built a rigorous 3-version pipeline. Tested 11 models under identical conditions, used 6 beyond course technique, and demonstrate honestly that after all of this, the bottleneck is the data, not the algorithm. The key finding from the report is when a stricter, more expressive, more leakage-safe pipeline does not dramatically improve scores, the data is the limiting factor. So here are what we have for today. Thank you for having us today.